Okay, welcome. Continuing into chapter 5, looking at the big one for this particular chapter, the big one being the fundamental theorem of calculus. All right, so in every class, almost every class, especially the algebra and the calculus sides, we have fundamental theorems. This is kind of, I always think of these as just like the basics. It's so important that it can't be missed. The fundamental theorem of algebra, if you remember, it basically says if you have x squared plus 3x plus 7 equals to 5 or whatever, you're guaranteed two answers. That's usually what we get out of it. The fundamental theorem of algebra actually has a much different meaning than this, but what we get out of it in our study of algebra, for the most part, is this statement. Getting two answers. All right, it's fundamental to us. All right, so in today's stuff, we have the fundamental theorem of calculus, and this deals with antiderivatives and integrals, definite integrals, and how to calculate them. And obviously down here you see area, net area, antiderivatives, all that sort of stuff. All right, so fundamental theorem of calculus, part 1. There are two parts of this theorem, and part 1 states if f is continuous on a function or on an interval from a to b, then the function f of x is equal to the integral from a to x of f of t dt. And we've kind of looked at this before in the sense of saying, let's go from, I don't know, 3 to x of f of t dt. It's just going to be f, basically, actually, sorry, that's the different one. We could find the antiderivative from 3 to x. Okay, that's my fault. That's the first part here. That's the second part that I want to look at here. We're saying that if f is continuous, then this function, the antiderivative, saying if we were to take the derivative of both sides, so we could take the derivative of both sides. The derivative of f is df dx, and the derivative of the right-hand side is going to be d dx of the integral from a to x, and I'm going to be pointing this out, a to x. And a could be anything, absolutely anything, as long as it's a number. And x has to be on the interval from a to b sort of thing. All right, so we can find the derivative of the integral by saying it's just f of x. I'm pretty sure I have an example up here. All right, so get this written down. We will see what this looks like in a second here. So what does this mean? Good question. I'm glad every single one of you asked that. All right, so what does this mean? We can find the derivative of these integrals by doing a very simple thing. We look at this and say, okay, this derivative is from a number to x. And we know that negative pi is on an interval that's continuous for cosine of x, so that's okay. And we'll just say, okay, well, this actually ends up just being cosine of x. Well, that seems kind of too easy, and it kind of is. But that's actually what this theorem is telling us for this first piece. We could just rewrite it as this, taking the derivative from negative pi to x of cosine t dt is cosine of x. Wow, nothing hard there at all. Well, the other case is just super easy too, because if I start at some value a, we're assuming that this is continuous on values from a to b already. Well, that just means this is just 1 over 1 plus x squared. And you're thinking again to yourself, this is too easy. And you're right, it is. But what happens if we look at problems like this? We're going to find dy dx, so we want to take the derivative of both sides sort of thing, right? So I want to find the derivative of this integral from 1 to x squared of cosine t dt. And some of you might be sine of x dx. Actually, some of you might even go, oh, well, it's x squared, so it's got to be x squared. Sadly, it's not the case. You actually have to think of something, or think about something that we haven't thought about in a while. Some of you haven't thought about in a while, and it's the chain rule. So what I need you to note here is if you have the integral from a to u, where u is a function, we have to do some extra stuff. So if I want to find dy dx, it's actually going to be dy du times du dx. And some of you are like, what does that mean? Well, I'm going to look at it like this. I'm going to say, okay, well, it's 1 to u of cosine t dt. And if I was to think about what's dy du then, well, dy du is going to be exactly as before. Instead of using x, it's a u. So here it's just going to be, okay, well, it's cosine of u. Oops, no d. It's going to be cosine of u. But here's the problem. I have to multiply by du dx. Well, in this case, u equals x squared, and du dx is 2x. The derivative of x squared is 2x. So I actually have to multiply this times du dx. Well, that's not too bad. Derivative of u with respect to x is just 2x. And then I have to replace u with what it was to begin with, and I get cosine of x squared, and I'm going to put the 2x out in front to not get confused. Oh, that's it. Oh, I don't have to do anything more, and I hope that's what you're kind of saying in your head too. Oh, that's it. So pay attention to what we did here. I let x squared be some new function u. I followed the same rules as before. I just said it's from 1 to u of cosine t dt. But using chain rule, if I want to find the derivative of a composite function, chain rule says, okay, I got to find the derivative of the integral times the derivative of the inside function, or of the x squared. So I get, very simple, derivative of x squared is 2x. The derivative of this integral is cosine of u. And then I just substitute in my u for x squared. All right, so let's see what that says for problem number 2 here. Now, I purposely made, or actually used, this problem because it's a very good problem and one that you need to kind of pay attention to here. You'll notice that neither of these values are numbers. They're both variables. They're both functions. Which means you need to do some splitting. You need to split this up a little bit. So I can say y is actually equal to the integral from, I don't know, let's go 0. 0 to x squared. And plus the integral, and you guys might remember these integral rules here that we had, from 2x to 0. Of 1 over 2 plus e to the t dt. Okay, so how does that help us? Well, what I'm going to do here actually is I'm going to change this a little bit because my fundamental theorem says from a to the function, not from the function to a. So I'm going to switch the order here, and I can switch the order. So I can go from 0 to 2x as long as you change it to minus, because flipping the order actually creates the negative value. Well, now I can use the fundamental theorem. I can use the fundamental theorem twice here, use it for the first version and the second version. And what I hope you're paying attention to is these are functions, so I have to use the chain rule again. And some of you getting good at the chain rule, I know, well, I can say, okay, du dx for the first one is going to be 2x, And du dx for the second one is going to be 2. And here we go. So the derivative of the first integral is going to be the integral times the derivative of u, which was 2x, minus the integral again times the derivative of the other one, of the 2x. And, oops, sorry, I forgot to put in the u's here. I'm not paying attention to myself because I was trying to combine the fractions. I can't do that. Here we go, erase those things. It's not to the x power here, and here's where you got to be careful, where I was not being careful. It's not e to the power of x anymore. It was e to the power of u, but u was actually x squared here, and u here is 2x. And obviously you can get rid of these 1s if you don't like them, because it's just being multiplied by 1. And there you go. There is your solution. Not too bad once you get the hang of it, obviously. That's usually how math works. It's not too bad once you get the hang of it. Just takes a little bit of time. All right, so let's look at the fundamental theorem of calculus part 2. The sequel. Not really. The fundamental theorem part 2 is actually one we've kind of been dealing with already. We just haven't called it this. We've kind of defined it. If f is continuous at every point on the interval from a to b, and if the big F is the antiderivative of little f, then we can say, okay, the integral from a to b, so basically saying something like, okay, the integral from 2 to 7 of, let's go 2x. Let's not do 3x. Let's not make it too difficult here. Is equal to, and here's where you're going to start seeing some notation. Actually, I'm going to, well, I'll talk about it in a second. This is saying, okay, what's the antiderivative of 2x? Well, the antiderivative of 2x is x squared, because the derivative of x squared is 2x. And most of you guys are getting the hang of this. So I can say it's actually 7 squared minus 2 squared is equal to 49 minus 4 is 45. And obviously you could figure out the trapezoid and find the area, but that's kind of painstakingly long. But what I do want to show is kind of a symbology that we use. And they didn't really introduce it in the textbook just yet, but I'm going to introduce it now. So, oh, I guess they did do it. I just didn't show it here. All right, so if I said from a to b of f of x dx is equal to big F of x, and this particular textbook uses square brackets, and they say a to b. Well, this statement right here is say, okay, take f of b, take the top one, minus big F of a. Now, often or sometimes I've seen it written like this. I've written it like this before. Take f of x evaluated on the interval from a to b. But we'll go with the textbook's terminology, the textbook's symbology here. So if I was to start with that problem I just had, 2 to 7 of 2x dx, I could write this as, okay, the antiderivative of 2x is x squared, and I want to evaluate from 2 to 7, and then I'm going to get the same thing, 7 squared minus 2 squared, 45. It's a good thing I got the same thing because it has to be the same thing. All right. There might be times in here where you have to think about total area compared to net area. And that would be along the lines of, let me get rid of this stuff off the bottom here. That would be along the lines of a function that kind of does this. And we could look at the area here. Let's say it's from 0 to 7. And I could look at total area, where I would have to actually look at what's the positive amount of area in here. Well, you're going to have to figure out what this intersection point is, and you're going to have to do this. But for the most part, we don't really deal with it. We deal with what's called net area, and net area is just what's the total area here. This being positive area, this being negative area. What's the net? What's the overall? And what you could actually figure out is, what I mean by this is if you did this, if you did 0 to 2 pi of sine x dx, what we're looking at here is the function from 0 to 2 pi. Well, I know I have one bubble above and one bubble below. That should cancel out. And it will, because the antiderivative of sine is negative cosine of x from 0 to 2 pi. Says, okay, take the negative cosine of 2 pi minus the negative cosine of 0. And cosine of 2 pi is 1, which makes this a negative 1. And cosine of 0 is 1, so it's minus a negative 1, and I get 0. So notice they will cancel out. Using this formula, you create net area. What's the total area is something a little bit more in depth, more in detail. All right, so let's see here. Oh, I forgot I had this on here. This is also called the integral evaluation theorem. I don't know why. I kind of like fundamental theorem of calculus much better. But it is the way to evaluate an integral, so they'll use the name theorem here and that sort of idea. All right, so let's find the area between the curve and the x-axis using antiderivatives. Now, you notice I wrote this in a little bit different fashion. You need to know that this statement, find the area between the curve and the x-axis. Now, before any of you come and ask me and say, hey, mister, this isn't a curve, it's a straight line. You're right, but we call all functions curves, right? Even straight lines. So what I want to point out here for y equals 2 minus x from 0 to 3, it's basically asking this. This is what I want to know. This is the question here. Find the area between the curve and the x-axis. And I'm saying area. Whenever I say area, you assume net area. The textbook's actually going to ask you find total area. And total area is going to be the positive and the negative both being positive. So you'd actually want to figure out if there's any intersections between here. All right, but let's just stick with this. I could say, okay, the antiderivative of 2 minus x is going to be 2x minus 1/2 x squared, evaluated from 0 to 3. Well, in this case, I plug in 3, I get 6 minus 9/2 minus 0 minus 0. So it's 6 minus 9/2. 9/2 is actually 4.5, so I get, or if I think about this, this is 12/2 minus 9/2 is 3/2. So what I want to point out here is the area. I'm going to get rid of this because I don't want you thinking about that. The question I'm asking is 3/2. This is net area. But you'll notice in the answer in the book, it's going to be different. Not even going to tell you what problem it is because you'll find it eventually. Okay, so you'll probably have to figure out any intersections and figure out the positive area and the negative area and treat them both as positive. For this particular one, I think most of you are probably getting this. This is going to be, okay, here you go. Here's the integral from 0 to 2 of the function 2x to the third minus 6x squared plus x dx. What I really want you to do right now is see if you can create, and some of you guys are getting good at this, like I said, see if you can create the antiderivative of this. So take a second, find the antiderivative, see if you get the antiderivative that I get. The biggest things about antiderivatives here is that you have to pay attention to make sure what you got has a derivative of the original piece. And if I took the derivative here, I should get 2x cubed. I get a 6x or a 6x squared, and I get just an x. So that means I got the right thing. And I'm sure you could evaluate this thing here at 2. Basically at 2, by the way, because the 0 just makes the whole thing 0. All right, so you guys might have noticed on the quiz that you guys just took some antiderivatives that are very handy, like let's just go from, actually, let's do this. Let's like 1 over x dx. Let's go from a to b, just to be safe here. The antiderivative of 1 over x is the natural log of x. So it's one of those good derivatives that you need to know. The derivative of natural log is 1 over x. Things like this. This is kind of a harder one, but I think most of you got it, just being, what, tan inverse of x? All right, the antiderivative of x is 1/2 x squared. All right, these are just handy things, so really try to figure these things out. Don't always just go to the answer key. Don't always just go to a neighbor, but really try to figure these things out. All right, you guys have an assignment sheet. I will see you guys tomorrow.